Okay, welcome to lecture number 13 in Introduction to Lattice Boltzmann, which is the final lecture of this series. So the fact that you are still coming here means you're difficult to chase away. So for this reason, we'll today get to a topic which is potentially a little bit over the top. So it's a bit more advanced, and I will potentially end on say open question. So the thing is, I'm giving this lecture for a few years now. This year, in the preparation, the last time and the time before, I did the calculations, and every time I get a different answer, which is a very bad sign. Yeah. So I'll just pretend that the answer that I get today is the answer that is correct. So you can look at the previous recordings and see what answers I get there. It's an advanced topic with interesting consequences. Maybe if you want to clean it up, you can have a master thesis on this. Yeah. If you are so inclined to stay with this topic. Okay, we're talking about magic parametrization. So this is already a bad word in science, but that's actually how people who were studying this in the 90s were originally calling this. Later it was called quadratic parametrization because people didn't like the word magic, but I'm now sticking to the old-fashioned magic parameterization. So, and this has been successful for some Navier-Stokes Lattice Boltzmann kernels, but we're trying it out for something where it's still kind of a little bit an open question, as I said. At least it's not validated that this is possible also for diffusion equation. Okay, so what we are coming, so we need to go through several steps to get there, but I don't want to, I try not to do too much small talk today because there's a lot that we have to cover. So, in principle, you have learned a lot here, and with this, you should be able to develop new lattice Boltzmann methods. And this is what we are going to do today. We give us two challenges. So kind of two assignments. So we have solved the Navier-Stokes equation. We do something pretty much simpler. We want to solve just a diffusion equation, yeah, which is of course a simpler problem. So we say we are going to derive a lattice Boltzmann method for the diffusion equation in two different ways. We are doing this in 2D so that we can also implement it in our code. So this equation will be the time derivative of some quantity C is equal to a diffusion coefficient into the Laplacian of C. Yeah, that this is a diffusion equation. Yeah. So the two challenges is developing a model for this, first as simple as possible, and B, as accurate as possible. Well, I mean, this is, of course, there's always, you can always get more accurate, but let's see as accurate as we can deal with it in this 1.5 hours. Okay, so the thing that is going to help us in developing new models is our asymptotic analysis. Yeah, with the asymptotic analysis, we can actually derive directly we can derive a parametric equation that is solved by our Lattice-Boltzmann method, and by fixing the parameters in this equation, we can get to any or some of the partial differential equations that we could try to solve. So now we are returning to our asymptotic analysis. And I'm going to call this 13.1 and repeat what we've already learned. So we are not going to derive this equation. We are using this equation the asymptotic equation to derive something, but we are not deriving it yet again. You remember there are two steps. There's a Taylor expansion and there's the asymptotic expansion, yeah? So, and the Taylor expansion, we are doing this in 2 dimensions. So we have 3 dimensions in which we do the Taylor expansion because we have 2 dimensions of space and 1 dimension of time. Let me see, the dimension of time I index with m, and the other 2 I index with n and l, and I let them start from 0, and we go to infinity. So now usual Taylor expansion, m factorial, n factorial, L factorial. Then we use diffusive scaling. So we have our epsilon by the power of 2m, yeah, because this is where we have time, yeah, plus n. So the other one, space is, so we have space, L, and we have in addition the expansion of the asymptotic expansion of the moments. So this we divide by 2. Okay, right. So because we do the Lattice-Boltzmann, we use this symmetric form of the Lattice-Boltzmann equation where we go half step. Yeah, we have this 2 here, and we have half time step. This is 2 by the power of m, and half grid spacing L, m, n, and L. So these are the prefactors. Then comes the derivative. So this is dt, as I said, with m, dx with n, and dy with L. So now this equation does not fit in one line. Yeah. So let me see, maybe I get the first part here. So we have the average moment. The average moment we indicate by this overbar, and we count them up with the derivative. So this is a plus n, obviously, and b plus L. Yeah. And we expand this with q. And then there is another factor 1 minus 1 n plus L plus m. So this is the moment, and then so this is pre-collision plus post-collision half, yeah, and then we also have pre-collision minus post-collision minus pre-collision. This is what we called omega, also expanded to q, a plus n, and b plus L. And here the factor is similar, just there's a different sign here. Minus 1 n plus L plus m. So, I mean, what you basically observe due to this here being a minus and this here being a plus, so every second time the one is turned on and every second time the other one is turned on. Now this is the equation that we had in previously. This was lecture 6, and I think this semester was lecture 8, yeah? So if you have to go back. Right, so the reminder, what we did here is Taylor expansion in space of time of the lattice Boltzmann equation and asymptotic expansion of the moments. By the way, the asymptotic expansion of the moments is kind of not important for what we are doing today. I think I've mentioned this, but can you remember why we usually need to have this asymptotic expansion of the moments in addition to the Taylor expansion? Because you can also do analysis only with Taylor expansion, and lots of people just use Taylor expansion. But there is one reason why, in addition to this, we have the asymptotic expansion too. So the asymptotic expansion helps us with also classifying the asymptotic order of nonlinear terms. Yeah. So because we have in the Navier-Stokes equation, yeah, we have, and with diffusive scaling, we have the expansion of u, and u being first order, yeah, such that u square is second order, and u cube, yeah, is third order, yeah. So this is required to actually sort out, they balance out the different orders with the different derivatives. So the asymptotic expansion is necessary for the Navier-Stokes equation because we have a nonlinear system. And this is the good thing with this kind of expansion, because we can analyze nonlinear equations with this. So today we actually have a linear equation, so it's not strictly required, but because we are used to it, we're just using the same method. So what works for nonlinear equation also works for linear equation. Okay, maybe, yeah, because the funniest thing, I was asked by somebody, well, you don't really need this. Yeah, why are you doing this? It's always important to remind yourself why on earth are we doing things? Yeah. It's also things that I'm going to ask in the potentially in the exam. Yeah. So why are we doing this? There's often reasons. So what asymptotic of the moments helps with non-linearity. For linear problems, it's not really required. Or Taylor expansion is enough. So if you ever try to solve a linear problem and this is why did we do this asymptotic expansion in the first place? I have a bad handwriting today. Okay. So our starting equation was, of course, okay, just a few reminder, maybe it's not, I hope you're still remembering this. So we do this time and space symmetric form of the lattice Boltzmann equation. That basically looks, I forgot delta x 1/2 and t plus delta t naught square half. Yeah, and this equal to 0. So this is what we Taylor expand, and since we put everything on one side, the entire thing, yeah, has to come out as 0 always. Yeah, and just to be self-contained, Eij, this is of course the vector of I and j, and we use delta t as proportional to delta x square proportional to epsilon square, and this is diffusive scaling. Okay, so this was all in lecture 8. So then we are going to use some sort of relaxation time ansatz, which is either single relaxation time or multiple relaxation time. Actually, today we will use some multiple relaxation time. So this is either BGK or MRT style. Yeah, so we will basically say that there is the moment MAB after the collision is equal to MAB before the collision plus omega, here comes an equilibrium, AB equilibrium minus the form before the collision, yeah? So omega is the state after the collision minus the state before the collision, and we'll write the average. Okay, this is all repetition now. The average, so the pre-collision state is the average minus half the collision, and the post-collision state is the average plus half the collision, meaning that MAB. So when we plug these things into this equation up here, what we get is MAB average omega. So we plug this here. No, we plug, that's my mistake. Yeah, so we plug this here on this side is equal to MAB minus omega AB half plus omega MAB equilibrium minus omega AB average plus omega AB half. So this is from plugging in this here, so we'll have twice minus, and then we bring everything, so we solve this for MAB average, and we get MAB equilibrium minus 1 over omega minus 1/2 omega AB. And this thing here will be our physical relaxation time, tau. So now this is what you've already learned here. So there's nothing new in this. Good. Now, if we want to build a model, an arbitrary model, or if we design a model, we have to make some choices, and we actually have choices. So it's not all the same. So we have to make a choice on the conserved quantity and its asymptotic order. So I remind you, that's not necessarily trivial, yeah? And there's not agreement, by the way. There's not agreement with the researchers. So here in this lecture, we choose for the velocity, we choose first order. In diffusive scaling, other researcher choose zero order. And that usually leads to acoustic scaling. And depending what you want to do, for example, you want to solve acoustic problems, then you want to have velocity as first order, then you're solving a different problem. Yeah. So there's not a unique choice. Now the choice we are going to make here is that we say that M00 of zero order is also conserved. So basically this is what that means, yeah. So this is conserved, and this we call C. This is our solution that we want to have. And okay, to be consistent with the later part of my lecture, I will write this here also to zero order, but zero order of C, this is what we want to have our solution. Yeah. So now we made the decision that C does not change with epsilon. Which we have to deal with in with our initial and boundary conditions. Yeah. So basically, you always have to remember if you want to follow this thing and in the Navier-Stokes equation, the principle, you do grid refinement, you also have to reduce the velocity. Otherwise, you're not solving the equation that you derive in this way. Okay, now we actually have a deeper look on our equation 13.1 to see that this can be restated in recursive form. So I think this we have not yet addressed in this lecture series. So one thing that we do right now is we insert the relaxation approximation. So this is something that we are going to assume. This means we are doing a substitution in this equation where we have this MAB over bar. This will become MAB equilibrium minus tau AB. So there could in principle be different for the different moments. Therefore, BGK it would all be the same. Times omega AB. Yeah. So this is what we are going to replace. And then our equation, I've not beautifully written this. Okay, let me write it like this. So now we want, okay, we are interested in make the following statements. We want to have the leading term in our equation 13.1. So the leading term in the equation 13.1, I'm always told never scroll back. Now I'm doing this. Never scroll back. Yeah. Okay, so the leading term is when all of them are 0, right? So when all of them are 0, then m n l is 0, yeah? This here is 0, -1 to the 0, this will disappear. So, but you'll have, oh, by the way, there's a mistake. Oh my God. Divided by 2. This must be divided by 2. Good thing that I scrolled back, right? So, divided by 2, please correct in your notes. So, now we get this here by the power of 0. So, this will be 2 divided by 2. So, we'll just get this guy here. Yeah? So, this guy is indeed the leading term in this equation. And this leads us, maybe I'm not rewriting this because I now find this a little bit confusing. I will instead write the following. So we have omega AB, say to some order k, at some order k, can be written, so because the entire equation sums to 0, right? So when I want to have this guy here out of my equation, what I have to do is to put this on the other side of the equation 2, which looks stupid in the beginning, but we'll see where this is going to. Yeah. Then you remember we can separate what's it called in Koeffizientenvergleich, equating coefficients, right? So what we are doing here is, so the entire equation that we had comes with epsilon, and we are interested in the case of epsilon, the part that's epsilon to the power of k. Yeah. So what I'm doing is I multiply this by epsilon to the power of minus k, and now comes here my equation, where I have m, n, l, and not plus, but and q. So I'm summing over all of them from 0. And now I only want to have the part that comes with epsilon to k out of this equation. Yeah. So I'm not summing to infinity, but I'm basically summing to the case. Now never scroll back. Now never scroll back. I'm doing this. So we have here 2m, epsilon by 2m plus n plus l plus q, right? So what we can do here is to say, so this sum has to, so we are summing over all of them, however, only for the case that 2m plus n plus l plus q is equal to k. Yeah, that's the sum that we have here. And then we get all of this thing here, 1 over m factorial, n factorial, l factorial. Yeah, here comes epsilon by 2m plus n plus l plus q, which you easily identify as being just k, such that this will disappear here. And this divided by 2 by the power of m plus n plus l. All of this into dtm dxn dyl. Okay, I should probably make the brackets here. And now here comes the, here's originally we have this m over bar, which we've just said we are going to substitute up here with m a b, no, sorry. That's because we're going in n. So it's n a plus n, b plus l. So, and this is the equilibrium, and it's of the order q. Minus tau omega, also of the order q, a plus n, b plus l. This, all of this multiplied with 1 minus 1 n plus l plus m, and also minus omega q a plus n, b plus l. Don't forget this 1/2. 1 plus minus 1 n plus l plus m. So now what is going to happen? Yeah, we saw that for the part that m, n, l, and that m, n, and l is 0, which means that q would be equal to k. Yeah, all that is left is this omega with a minus. So basically, this leading term, this omega will eliminate this omega. Yeah, and by this, we now build a recursive equation for the omega. Yeah, so this equation will give us the value for the omega AB at the order k. So why is this important? It is important because we have it back here. Yeah, so we can put this equation into itself, yeah, to get further and further and further equations until they disappear. So why would they disappear? Okay, I have a few notes to write down, so and that they will be in the writing. So we do, as I said, equating coefficients. Equating coefficients, epsilon is larger than 0 is arbitrary. This means that each order AB and omega A, B, K, and M, A, B. So this is also very important. It's also true for tau. Should probably try this for tau. Yeah, as I said, this is a big mistake that is sometimes done. If you use acoustic scaling, then tau is a function of epsilon. Yeah, no, you cannot just treat this as a constant. Yeah, so then that would be, I mean, it's constant for a given resolution. Yeah, but it's still a function of epsilon. Yeah. Yeah. So the important thing is they must not. What am I writing? Not depend on epsilon. Yeah, that's very important. So I'm running out of space. So since they are not allowed to depend on epsilon, we have to restrict the sum to terms of order epsilon to the power of k. Yeah, so basically meaning only the terms in this equation that are of the order epsilon k actually matter for this, all the others drop out at this stage. So then we've seen that this is a recursive equation. So 13 points. Did I give this a number? No, I did not. Let's give this a number, 13.2. 13.2 is a recursive equation with omega a b k pending on omega a plus n, b plus l, and q. So, question, is this a problem? So that could be a problem because when we apply this recursion, we want this recursion, of course, to converge. So would this converge? Why would it converge?
Because they have definite values at the beginning.
Definite values at the beginning. I think this is not the reason why this converges. The reason, okay, well, look at what is the reason for this converging. Yeah, see, we have, so the sum of 2m plus n plus l plus q must always be k, right? So now we are counting upwards n and l. When you're counting upwards n and l, so I mean a, b, so the lowest order that we have, so actually the lowest order would it be itself, but this will be eliminated through this, right? So we only have terms that have that are higher in n or higher in l, so that have a higher index here. So when they have a higher index here, they will automatically have a lower index here because the indices have to, has to sum up to k. So that means they are only dependent, so the omega of order k is only dependent on omegas of order lower than k. Yeah? And since the lowest order, we derived that k to the order, that omega to the order 1, and in particular omega to the order 0, is 0, yeah, so this is guaranteed to converge, yeah. Right, so let's write this down for, since q is smaller or equal to k, is actually, okay, I should say it's actually smaller than k, yeah, it's not, it's really smaller than k. In 13.2, the recursion converges. Okay, so the thing is, there's another excuse why I always get tangled up with the result of the recursion can be very big. So it's usually not very straightforward to do this by hand. And actually, I remind you, one of the first things that computer algebra ever was used for was analyzing lattice Boltzmann. Yeah, so this is Stephen Wolfram and his Mathematica. Actually, it was the predecessor of Mathematica. Yeah, so they said we derived the Navier-Stokes equation for the lattice gas automaton, and there is a quote from Stephen Wolfram saying that if lattice Boltzmann does not solve does not solve the Navier-Stokes equation, we should forget the Navier-Stokes equation. Okay. Right. So, how is the time? I thought about this. Okay, last time, since you're so eager to know things, we are now going to actually trying to do this. What do you think? This is part of the exercise. I don't know. I have a lot of exercise prepared. I'm not sure we get through this, but today is the last the last chance. Okay, we are. This is very difficult to do this without computer algebra. So we are trying to use computer algebra. I think probably we need more space. So we'll have an omega, and we'll give this the indices A. So now you need a little bit. I hope you're a little bit familiar with mathematica by now, yeah. But I'll talk you through. So this index is a variable because I put this wildcard here, yeah. So B. So I cannot make the other index. So what I'm going to do is I write I just use a bracket, yeah, to indicate that this is the order. And in order for the derivatives to work, we also have to indicate that this is a function of x. What's happened? I pressed the wrong button. Huh? X, y, okay. X, y, and t. So we have to indicate that this is a function of x, y, and t. And now we define this as, so now I have a little bit of problem. I want to kind of steer my recursion. So when I do the recursion automatically, it may be too eager, yeah? So in order to steer this, I will first write the other omega as ohm, yeah, so that I can later replace it, yeah? So I'll just write ohm here, and okay, maybe I should do one thing first before I go there. We are dealing with a lattice, and in the lattice we have this aliasing problem, yeah? And you know that we are now counting up these indices, and when we count over to 3, then we would like to return to 1. So in order not to confuse this, I'll make here a function, call this psych, and giving this n. So this is supposed to say if n is equal to 0, then it should return 0. Otherwise, if it is odd, so I can ask whether it's odd. If it's odd, then it should return a 1, and it is even, it should return a 2. Okay? So this is how I build in my aliasing, because it's relatively simple. I built in my aliasing in this. So I'm going to use then for everything here psych A and comma psych B. And then we have k, I guess. Yes, now we have k. And don't forget that this is a function of x, y, and t. Okay, so that's the first part that we had here, just to remind us about this equation. So that's this here, yeah. Then, okay, you see this here is already here. So I forget about the epsilon. And now the the interesting bit is how do I get this here into the equation? Now, I will make it relatively simple. I will just solve this more or less for Q, and I will replace Q by K minus 2m minus n plus L. Yeah, that's what I'm going to do. So now what we need here, we need to get plus the sum over, now we get this prefactor. The prefactor is 1 over, okay, I'll put everything here. That would be m factorial times n factorial times L factorial. And then we have times 2 by the power of 2 times m plus L, 2 plus, actually, should I, here, L plus n.
Not 2 times n.
2 times, no, not 2 times. Yeah, you're right, not 2 times. Yes. Yeah, that's only here. Right, yes. Thank you. So, and now closing this. Now we also have to set the derivatives. Now, since, okay, so there's one thing specific to mathematica, and when we now take the derivatives, and then we want to do recursion, it will not interpret this function anymore as the original function. So I also have to stop it from applying the derivative. I'm doing this in a similar way. I define my own derivative as dd, and later I replace this. Yeah. So I'll write dd, and now comes everything else here. We have the okay. Am I going to write meq? Okay, I'm writing meq. What no? meq. So then comes here psych. We do a plus n, comma, psych b plus L, and now comes the q. Yeah, and as I said, the q, we define the q now as the we take k minus the other guys. This is k minus 2 times m, see my cheat sheet, minus n minus L. Okay? And this is, okay, this looks crazy. And this is also a function of space and time. Yeah, so we have to indicate this. Okay, so then we have to do one thing here. Minus. Okay, for the time being, I will change this later. I'll just write tau. Yeah, I'm going to change this. But for BGK, it would be tau for all of them, right? So tau times, now comes again this omega, and this omega, you know what? This has, okay, I'll do it. So this omega looks the same as this. It's just omega. Yeah. So, why did I put the bracket here? That's not correct. So putting the bracket here. And now I have to multiply by this thing here. So this is 1 minus 1 n plus L plus m. Okay. So now we have this. So this is the first part here. Now comes the second part. The second part has this thing here again. bracket, closing bracket, thank you. There comes a minus, then comes this guy by 1/2, don't forget it, yeah. 1 plus, okay, so it's basically the same thing here, just with a plus. So we take this. So we are running a little bit out of the picture. So what I said, this is this with plus here. And now our derivatives. So I indicate my derivatives. I write the same nomenclature so that as Mathematica uses derivatives, we have x. X takes x takes n, so nth derivative in x, the lth derivative in y, and in t we have m. So that's our derivative here. And now we have to do our sum. Our sums, again, we have to do 3 sums, and now you can think about efficiency, which we are not going to do now. Yeah, we are summing over n from 0 to k. I'm just doing the whole thing, and then I'm throwing away what we have too much. Yeah, I mean this can be done more efficiently, but this is not what we're dealing with today. So, and then with L. Okay. So I should have potentially, is there LBM, yeah. It's already an asymptotic analysis, and recursive. Okay, now we implemented our function here. We are going to improve it a little bit, but just give it a try. Yeah, so we get omega, not that omega, big omega. I mean, actually, omega means big O, yeah, instead of omicron. Yeah, so there's a big, so a little omega is. I promised I'm not doing small talk. Sorry. So say we do this for 0 order. What do we need? X, Y, and T. Something coming out. Okay, so we get a few things out of here. Yeah. So now we'll see that. Now we are doing a little bit of simplification in our definition here. So this here is the 0 order derivative. Yeah. So if we have a 0 order derivative, my suggestion is we are not considering, or we replace this. Say we have. Now this is something that we can in Mathematica do simply like this. So yeah, so there's something in the 0 order derivative, and we put this. So that's stupid. Not like this. Not like this. Sorry. So we'll take something, yeah, that's taken the 0 order derivative. So it's the thing itself. Yeah. So okay, let's do it this way. Now, we will get this out, and then we'll have 0. Yeah, that's what we want to have. Now also, since this is a recursive equation, we need to be very careful, yeah, not to run into infinite recursions. So for this, we will also do an elimination of things of the thing, first of all, the moments, so MEQ, and say they have, again, AA something, BB something, and K, no, not K, KK something. I cannot use K because this is the same line, yeah? KK something in X, Y, and T. Now, what I'm going to do is if this is smaller than, if this goes negative, yeah, then I know it doesn't exist, yeah? So I'll get that if KK is smaller than 0, then it's 0, and otherwise it is the thing itself. Where I have to get rid of these things. So, and the same thing I'm going to do for, or maybe I can simplify this. Okay, I can actually simplify this by saying something. So then it will also apply for the collision operator, Then it will also apply for the other one. So let me see whether I have now been, okay, save. So going to second order. Okay, we go here. I make the suggestion that now this here is a bit annoying because it's taking a lot of derivatives of zeros. Yeah. So I'll get rid of this too. Say so suppose there is an 0, and here I actually don't care what is here. Whenever we take any derivatives of 0, my suggestion would be that 0 derivative of 0, that is the wrong, so, yeah? We are removing everything that is that did not work. So this didn't work. I don't know. Okay, let me see. Maybe I don't care what I don't care about anything coming later. Okay, now, okay, I apparently, so what was the reason for, okay, I used repeated replace. Apparently it did not fetch it at the first instance. Currently, I cannot explain why this happened, sorry. Yeah, so, but is everything else? What's about the rest? Okay, we still there's one magic thing that I have to there's one method specific thing. Maybe I do this in a second step. Okay, let's try. Let's assume this is our expansion here, or our recursive equation, and from this recursive equation, we now want to derive our so let me see. When we have zero order, we get nothing. With first order, we get these guys. By the way, there's no time derivative in this, as we would assume. So our assumption is that we would get the correct equation at second order. Yeah, that would be our target equation. By the way, I have to watch out for my so we will also have to not forget that we want to write a few things into the script. So we use for what happens. So for the zero moment, we got omega 0 to 0 order is omega 0 to 0 order minus omega 0 to 0 order is equal to 0, right? So now we do k is equal to 1. So this is what we just checked out. K 0 to first order is omega 0 first order minus omega 0 first order plus dx m10 equilibrium to 0 order minus tau omega 10 to 0 order. So this thing to 0 order, that would disappear. Yeah, so only we have this equilibrium thing here, and of course the other one, y m01 equilibrium to 0 order minus tau omega 01 to 0 order. So you have to remember that the equilibria, this is our choice. Yeah. So now we can define them the way we want them. Yeah. Okay. Now we will apply. Now we would have to apply that. This is what we also can do. What is the time? The recursion, yeah. So basically, we will have to look. See, we have this omega 0.1 in here, yeah. So what we need to do, in principle, is we go to. Now we just do a recursion. So when I go, so I put a semicolon here, and then I'll take the result by this percent sign, and what I'm going to do is I'm replacing now this omega with omega. Yeah. So this will hopefully replace this one here with this, and now what I get out is this recursion. Yeah. So I have, of course, here the next one with 0 in here. Yeah. So basically, this is due to my laziness, because I should have made it clear before here that any omega, I'm never sure that this actually works, that any omega to order 0 is 0. Let's see whether it's actually going to do this. So that should make this here disappear. No, it does not, of course. What am I going to do? Okay, I'm not sure why this. Okay, my cheat sheet has a different solution to this. You know, I noticed this using these indexes as function. This is sometimes it works and sometimes it doesn't, and I don't really know why. It's so what I'm going to do instead, I'm using this here. I'm MEQ. I'm writing MEQ just for this. MEQ, and so this will disappear when it's smaller than 0, and the other one will already disappear when it's smaller than 1, because it's 0 for let me see whether this, so smaller than 1. So let me see whether this now, okay, yeah, this will eliminate them. So now there is, in this equation, there is no more omega. Yeah, everything that is in this equation is something that we can design. So right, writing out what we are doing is recursion. So the recursion that we have to do is the script does this automatically. Yeah, it's putting a to 1, b to 0, and k equal to 0. So this gives us these things here, which are omega 1 0 0 order minus omega 1 0 0 order is equal to 0. The same thing for omega 0 1 0 is equal to 0. Yeah. So this means that basically we have omega 0 0 to first order is equal to dx m10 equilibrium to 0 order plus dy m01 equilibrium to 0 order. This is something that we have not yet identified here. So in order to get to identify this, so we have seen this. I'll go to the next line, take again the result of this, and do the replacement of dd with d. Yeah. So that gives us this thing here, where it has not eliminated this. Why didn't it? Okay, it will. Okay, yes, of course. So because this here, this here is only 0 order. Yeah. So in principle, we have these guys here left. Sorry, I know what's happening. Yes, so the equation that we just wrote down was for first order. Yeah. So that's the thing. I've gone ahead to second order. Second order is now looks a little bit different. So we'll get to k equals to 2. We have omega 0 0 to second order is omega 0 0 to second order minus. I think I'm going to skip over this because this is getting boring. So what we end up here is dx m 10 equilibrium to first order. I hope this is correct. Let me see. So gets right. So we get so this here is the order in which we take the derivatives. Yeah. So this is the y derivative of this, and this is to first order. So they come with tau omega 10 to first order. This is so here we still to first order minus tau omega 1 to first order. We've already in mathematica we've already did the recursion, so it's already replaced there. Yeah, plus dt m00 equilibrium to zero order minus tau omega 00 to zero order. Okay, so that's something we have to that can potentially lead to problems. We discuss this in a minute because this here is a conserved quantity, so this should disappear. Yeah. So, but we have to make it disappear. So again, we do a recursion. A is equal to 1, B is equal to 0, K is equal to 1. Yeah, so Mathematica does this automatically for us. What we see is that omega 1, 0 is omega 1, 0 to first order minus, okay, I said I'm not writing it again, I'm writing it again, plus dx m to 0 equilibrium now to 0 order minus tau omega to 0 order. So to 0 order it should disappear, plus dy m11 equilibrium to 0 order minus tau omega 11 to 0 order. And you know, similar, am I going to write this down? Okay, I'm wasting too much time. This, of course, okay, not this again, dx. So what was this? This is 1 equilibrium to 0 order minus tau omega 1 to 0 order plus dy m11, no, sorry, 02 equilibrium 0 order minus tau omega 02 to order 0. And these things, of course, we have already identified these two 0 order, this here to 0 order, they are all to 0 order everything, all the collisions are 0. Yeah. So, but this we've hopefully already built in here, and by them being 0, we see that the recursion has terminated. So now we want our equation that we finally get out, this 13.3, is that omega 00 to second order is dx m10 equilibrium to first order minus tau dx m2 equilibrium to 0 order plus the y M11 equilibrium to zero order plus dy M01 equilibrium first order tau dx M11 equilibrium zero order plus dy M02 equilibrium to zero order. So it's a good thing that the computer is doing all of this to us, for us, yeah? Plus dt M00 equilibrium to zero order. So this is in fact, hopefully, what we got out of this. So then we are ready to define our model, because this is the equation that comes out, and this equation does not yet look exactly the way we want it to look like. Yeah, so we'll have to make some decisions here to make it look the way we want it. So first of all, yeah, we design the model. Design the model. So M00 is conserved. This means M00 equilibrium is the same as M00 is the same as C, and also omega 00 is equal to 0. And all of this applies to all orders of this, right? So then we see that, okay, what do we want to keep? What we want to keep is, I mean, we want the Laplacian. So we want to have dxx, so we want to have this guy here. And we want to have yy, so yy would be that guy here. And this is related to the moment M20 and the moment M02. And we do not want to have this guy, this guy, this guy, and this guy, because they do not appear, these derivatives do not appear here in this equation. And because they are fully under our control, what we have to do is to put this guy, this guy, this guy, and this guy simply to 0. Yeah? So, this means we have no first derivatives in space, meaning that M10 equilibrium is equal to M01 equilibrium is equal to 0. And we have also no mixed second derivative. So which means that M11 equilibrium is also 0. And then, okay, then there's one, we want to have the correct second derivatives. So what we have in our target equation, we have delta. The Laplacian of C, which is of course dxx c plus dy y c. So that implies to us we have to specify M02 equilibrium as the same as M20 equilibrium, and we specify this as theta times M00, which is our conserved quantity. So now let's try to do this in mathematica. We have to do this before we take the derivative. So I'll put this in here in between. Put this in between here, and I now give this a list with the specifications of our model. Yeah, we have the moment. Okay, I'll take one of them. Okay, I have to get rid of this derivative here. So 0, 0 say to k, I will replace this by c k not, okay. Maybe that's not even necessary. So all the moments have to be specified now. So one we said should not appear here, so we set it to 0. Also the other one. 0. So then we have 1, 1. That's also 0. And then we have the 2, 0. And here we said this is supposed to be this times theta. Okay? And the same thing goes for the other one. So let's do it this way. So then, if we stay on D2Q9, we'll also have that one here. So for this, we did not see any constraint. So we can put it to something, but my suggestion, if we don't have a constraint on this, it makes absolutely sense to set this to 0.
And 1, 1 set to 0, there is a typo.
Yes, that's a typo. Thank you. That would have been a complaint. So the other one, in the other direction, we want to be isotropic. We want to be isotropic, so we put this here to 0, 2. Now question, what do we do with M22? So I'm a little bit undecided with regard to M22. Whether this is again related to C or not to C. So we let it open and give it gamma, and this gamma could also be 0, and then it would be 0. Okay. Zip. Okay, I should put a semicolon here so that we don't get confused by this. And now we got our equation. Yeah. Now we are actually done with this. So our yes, let us write this down. Our equation that we got is dt m0020 order dx tau dx theta. So mathematica will already put them in front because they are not functions of x and t. Yeah, so that will mathematica already decide this. If you make them functions of x and t, then they will appear in this order. Yeah. Tau dy theta m0020 order, and this is equal to the gradient of tau on the divergence on the gradient. And the divergence on the gradient is for tau and theta constant will give us dt m 0 to 0 order is equal to theta will now look like this, and our diffusion coefficient now is theta times tau, which is theta 1 over omega minus 1/2. Yeah. So, and we said for that M21, M12, M22 have no effect to the leading order. So we can choose this guy is equal to this guy is equal to 0, and for M22 equilibrium we choose gamma M00. Okay, now we can get some, so you can actually put this into BGK format, yeah, without moments. You get from the equilibrium moments. So we'll have the moments being MAB is the sum over IJ is equal -1 to 1 I by, so this is our definition of the moments with, we say that 0 by 0 is equal to 1. And now we can solve for populations. So since we have so much in front of us still, I'm just not showing this. This is pretty simple. So we say that we get lambda and sigma not equal to 0, and we have lambda, f lambda sigma is 1/4 M11 lambda sigma minus lambda M12 minus sigma M21 plus M22. We have f lambda 0 is equal to 1/2 lambda M10 minus lambda. Hope I'm not mistyping this, so it's not extremely important. If you want to verify, then just do it yourself. It's just solving. This is not an alpha, this is a sigma. M01 minus sigma M21 plus M02 minus M22. And the 0 part will be M00 minus M02 minus M20 plus M22. Okay. So you get basically the lattice weights for your BGK operation. By putting the equilibria, so with lattice weights Wij, so these are the populations at equilibrium. at equilibrium and m00 is equal to 1. So this gives us m0 times W11 is 1/4 M11 equilibrium. So this guy here is 0 minus M12 equilibrium. This guy is 0 minus M21 equilibrium. This guy is 0 plus M22, which is gamma M00. So we see that if gamma is 0, then W11 is also 0. Yeah. So for gamma equal to 0, W11 is 0. So what does this actually mean? This means if this is our that has been our previous stencil D2Q9, this will become, see, this will become D2Q5. So they actually, by this choice of gamma, we have eliminated some of the populations, and we do not need to store them anymore. Populations vanished. So something similar can be done with M00 times, okay, not this, M with W11, this will become 1/2 M10 equilibrium is 0 minus M, by the way, just to be complete. This here again is 0 plus M20 equilibrium minus M22 equilibrium. This becomes 1/2 theta plus gamma M00. And the last one, M00, W00, is M00 minus M02 equilibrium minus M20 equilibrium plus M22 equilibrium is M00 1 minus 2 theta plus gamma. So what now you could do is you can put gamma equal to 0, theta equal to 1/2, and that would imply that W00 would become 0. Yeah, which means you can also go from D2Q5 to D2Q4, and you can still solve the equation with F01 equilibrium, so with all of them being the same, just being 1/4 M00, or 1/4, okay, let's call it C, yeah, the C that we want to solve. So, and then you can write this as Fij asterisk is equal to Fij plus omega Fij equilibrium minus Fij input with D equal to theta 1 over omega minus 1/2 being 1/2 1 over omega minus 1/2. And this gives us then dTc is equal to 1/2 1 over omega minus 1/2 Laplacian on C. So, and as I always say, there is nothing new under the sun. This thing here is exactly the same as forward in time. So I think they write it big. Forward in time, central in space. FD solver. Just stated in Lattice Boltzmann format. Yeah. So, but it's doing exactly the same. So this was part. Sorry. Do you want to continue? I have everything for the end. I have enough for the entire evening if you want. So this was as simple as possible. Yeah. Boring. Now we want to have as good as possible. The good thing with this, we have prepared everything for this already. Yeah, because we have our machine that does recursive analysis. So I'm cheating here because we are not doing as good as possible. Yeah, because we are already over time. We just try to do as good as possible by using two relaxation time. So this is called TRT. This is something that we have not discussed here so far, but which is a very common model, and this assumes just two relaxation times, and that are split between the symmetric and the antisymmetric parts of the populations. Yeah. So assume relaxation time T odd for odd and tau E for even moments. So our target equation depends on the relaxation of the first moment. So it's the odd tau that comes in. Yeah. So our target equation comes in as dt m00 to order 0 is equal to tau odd theta Laplacian m00 to 0 order. So now a few observations here. That tau E has no effect on the target equation. Okay, so maybe you should believe me, or we should try it out. So here we had only one tau. Now we are going to do something else. We'll define a function in here, odd even. Now, because we have two indices, I get A and B. And what I'm going to do is I put there I'll ask whether odd q a plus b. Then I will just name this odd, and otherwise I will just name it even, okay? And what I'm now going to do is, instead where we had this tau, yeah? So this tau now becomes tau odd even, and it basically is related to this thing here. So I'll plug this here. Okay. Now let us apply this. Let us apply this. And it has not executed odd even because I did not put underscore, right? Yeah, so that's an annoying thing in math. So okay, we get this. We get this with odd. Is this what I said? So this is what I said, right? So, and we see there is no effect here in the leading equation of odd. This just didn't come up. So now, why are we doing this? The question is, what happens to leading order or the leading error? So in order to get to the leading error, we have to get to our recursive equation. And we start again with a equal to 0, b equal to 0. And now we go to the error. So we have a symmetric method. The error will not be on the third order, but it will be on order 4. Okay? So let's go there. I'll keep this here and just put this here and see what happens if we go to fourth order. Now you see that everything appears to get more complicated, yeah. And in particular, we have to do these replacements here again. I should potentially, let me see whether I can kind of, no, I don't think so. Okay, so you know, I need to repeat this here, and I'm now being lazy and just do it like this, yeah. So you see, we have not come to a conclusion so far. So I'm doing this. I'm doing this again, and now there are no more omega. Yeah. So now this is the equation that we solve for. So this is the equation at the next higher order. Deriving this by hand is a bit challenging, but we can use mathematica and it does it for us. So it's not, I guess it's not beautiful. So what I'm going to do is I will okay, I'll expand this, which I always have to do first, and then I will collect the terms that I'm interested in. So it's not collecting correctly when you don't expand first. So I want to distinguish these things with the different with the different derivatives. So here, for example, we get a forced derivative in 2 in x and 2 in y. So this is the mixed one. And then I have the ones that are not mixed, like this here. So let me just see whether this already does something. So, okay, what this does is collecting the prefactors, yeah, in here, and that's not yet beautiful. So we are kind of missing a few of them. Let's say I'm missing this one. And I'm also missing that one. I guess I'm missing that one. Zoop. So. Now what did we get here? So let me see. Here in the beginning, so we have here one thing. There is an ugly artifact here, and this is this one here, and I'm not actually completely aware of how to explain why this how this second derivative came here, but okay, the reason why it is here, and I'm trying, let us try to get rid of this. The reason why this is here is because we did not tell the method that the zero moment is conserved. So this actually comes from, this is an artifact somehow originating from the collision operator of the zero order moment. So in order to get rid of this, I basically now make the statement that, let me see where. Okay, we can either put this. Okay, I'm trying to put it here. Maybe I have to. So I build it in the expansion. If there's 0, 0, and something here, that should be 0. So now it's built into the expansion. Now it should not do anything here. And here we did not do anything here. Great. So this is one of the things I okay, that's potentially a guy that gives us a mistake. So how on earth? So let me try to find it on my cheat sheet. What did I do? It is T0. Say Okay, I believe what I did is this. Now, where am I? So I get when. So I'm now hoping that this is going to work, but if so, I don't know why. What was the sometimes the logic is and t. So this here is going to be 0, and the rest would be like this. So this will only catch, the second omega will only catch it when the first omega has disappeared. It does not work. Why doesn't it work? It's okay. Now I got stuck. Now we got stuck and we don't have. Okay, let me try to continue with the lecture, yeah, and say what is supposed to happen. So we got this equation here. So this is as I told you, I always get a different result when I try to do this. So what we have to do and what we have already done, we have including Aliasing. So this is M30 becomes M10. So this is already included. We wanted to include, and this somehow this is the thing that mathematica just didn't try to understand. The conservation that this is equal to 0, then we also, this is something that we are going to do, including all equations gained at leading order. And here my notes say now you really need computer algebra. Until there you could do it by hand. Yeah. So there is to this thing. Let me see. What is the outcome? We have. Okay, I'm now writing out the outcome that I had previously, and then we see whether we actually get this here. So I had 0 is equal to the 0 order of omega, and here I get dt m00. Okay, I don't need equilibrium anymore, say to order 0 minus tau 0. No, that's not, sorry. We get this to second order, tau odd theta Laplacian 0, 0 to, not to 0 order, but to second order. So this I call term number 1. Then we get plus 2 theta tau even tau odd minus theta quarter dt theta m00 equilibrium, not equilibrium, to order. Now this is a problem because this comes to order 0. I'll explain what this means. Can have a look here. So this is this here. So there is indeed something else in this place. So there's a second. So this is somehow related to this problem here that I cannot identify now. Okay, let me look at something. Okay, let me briefly. Okay, doesn't help us. You know, in a sense, that suppose the outcome is now not correct. Yeah. What I want to point out here is the procedure. Yeah, and doing this live during the lecture can easily lead to mistakes. Yeah. The problem with this procedure is if you make a mistake, your result will be useless. But I want to. What I want to teach here actually is how in principle you get there, and this you could also get if the result is not the right one. Yeah. So this is why I continue with my writings, and then we see whether we can kind of clean this up or not. We have gamma tau odd 4 minus 6 gamma tau even square tau odd, and this goes into this guy here, which is of 0 order. This, I guess, I call this term number 3. And then I have one more, and in my, unfortunately, mathematica gives us yet one more, which is not supposed to be here, and also these factors are not the same. And this will all be on the recording so that everybody can make fun of us later. M0, 0, 0 plus dy, so first order M0, 0, 0. So whether this is correct or not is now not the important thing. The important thing is the following. These things here, this up here to second order is exactly the equation that we want to solve. Yeah. So that doesn't hurt us. Yeah, because even we put something to second order in it, it will solve the equation that we want to solve. Yeah. So terms, this is the diffusion equation. M00 to second order. And this also gives us 0 if the initial and boundary conditions to this, which is under your control, if you make your initial and boundary conditions not dependent on epsilon, then, I mean, what you would by default not do, then this thing, so if you put them to 0, then the thing is 0, so it doesn't hurt you. So one thing that hurts you is this term number 2. This term number 2 is the time derivative of m00 to 0 order. And this, okay, so why does this hurt us? So these things here, this is a function of the solution. m00 to 0 order is the solution. Yeah. So we cannot. This is arbitrary because this is what comes out of the simulation, and this will not necessarily have a vanishing gradient, and it will not necessarily have a vanishing time derivative. Yeah. So this will generate. This basically will generate. Yeah, it will change m00 to second order in time because here is a source term. Okay? So, but this source term also depends on t. So we do not need to accept this thing. I mean, there's a time derivative in front of this. So what we can do with this is we can do a substitution of the target equation. Substitute. I cannot write substitution. Substitute with the target equation. So what does this mean? So we have dt m00 to 0 order is the Laplace. So we can exchange the derivatives here. Yeah. So we have the Laplacian of the time derivative of m00, and this is in our target equation. So we'll have this being basically this, and this we can put into 13.5. So the idea in mathematica, now where we have this problem that it's not working the way I wanted it, is you do. So we want to get rid of this thing here. Yeah. So we go after this and put here. We say that that this thing here, say is AA, BB. So anything of that kind, so any other derivative, yeah, would be derivative of this. Now comes our target equation. Now the target equation basically looks like this. Of course, to 0 order. Okay, I'll put. This was stupid. Okay, get the entire thing here, and so this is our target equation, yeah? So, and this we have x, and we have the derivative AA, and we have the y and the derivative BB. And we close this. Okay, was not necessary. So semicolon, and what this is doing, it eliminates, it eliminates this and collects this with, because now there's a fourth derivative, now it combines these things with these here. So if this would have gone the same way as it was earlier today, and I remind you, every time I do this, I get a different result. I mean, I actually checked this result against the result that I had 2 years ago, and this was yet a different. Unfortunately, otherwise, oh, this is now, sorry. So what now we have is 13.6 should be 0 dt. Okay, I'll try to figure out later what I mean. The thing is, I'm not asking for these coefficients. Yeah, I'm just, so we have the, this harmless part. Then what we should get is something like this. Somehow I was not able to, in the right place to tell it. So we get this part multiplied by the x, the fourth derivative of m0, 0 order plus dy fourth order m0, 0 to 0 order. So this is one part, and the other part is 3 gamma tau even divided by 4 plus gamma tau odd divided by 4 minus theta square tau odd divided by 2 minus 6 gamma tau even tau odd plus 4 tau square tau theta square tau even tau odd square, and this multiplied with dx square dy square m0, 0. Now we don't know whether this is correct, or I made a stupid mistake. Yeah. So the things here are not that important. What is important is what you see is that these two things here are the source terms. And if these prefactors, which I have here, these parameters that we can choose freely, if they disappear, then we have made this method first order convergent. Yeah, we eliminate, we got, next level, literally. Yeah? So that's the basic idea behind this. And so for the Navier-Stokes equation, there is such a solution that has been found after 20 years of trying. And it's also validated that this is the solution. Yeah, so this here gives null solution. I'm not presenting this here because this is extraordinary complicated. Yeah. M002. So that, when we eliminate these things, then m00 to second order will always be 0. And then we don't have the error, yeah? So this is true if, let me give this a name, say this here is A, and this here is B. No, not that here, sorry. That here. That here is B. So if A is equal to 0 and B is equal to 0. Now, in this, we have actually 3 open parameters. We have tau e, we have theta, and we have gamma. Yeah, so we actually have a choice of parameters that we can use. So, and now I'm so much in trouble because I did not get rid of this guy here. No, yes, because if I mean the idea behind this is, so as long as we still have this guy here, we cannot proceed. There is one last hope which I believe is wrong, and this is why we get, because we could also replace you know, I could make I could do something like this, which is very, very nasty. And put okay, so that was okay, so that eliminated it, but I think this is not entirely, this is not the correct way. So, but suppose it was the correct way. Yeah, the thing that we now would do is, you see, we have here the, I mean, we still have, so these 3 parts here are the original equation. Yeah, then we have these 2 parts here are the same, and then we have this part here. So what we would do is we would use solve, and I would take this guy here, of which appears twice, so I'll have to take it only once. I put this to 0, and I'll put this guy here and say this is supposed to be 0. And then I want to solve this for tau. I'm solving for tau even, and I would solve it for gamma. So, and then I will have this result here, okay, which is so much more beautiful than the one that I have on my script here. So I'm actually inclined not to write this down. So maybe, so but I believe this here is wrong. Maybe now we found the solution here online in this, I don't know. So one thing, okay, let's first continue here, and then so what you do is you solve for tau e and gamma. So the solution that I got is, I don't know whether it makes sense for you to write this down. So I got a very ugly solution. There's actually 2 of them plus, because there's a square root of 3 times 3 plus tau odd square minus 96 tau odd square plus 768, yeah, okay, cannot be right. Tau odd to the fourth order zip, and this actually is not completely out of the ordinary here. I mean, the solution can look like this. There's one interesting thing. Whatever I get for tau e, yeah, and you see, I always get the same thing for gamma. And I also got this right now. Yeah, we got the same. I mean, if this didn't come out, then I would know that the solution is wrong. Yeah, because actually this is what we expect to have for gamma. Yeah, if you think about accumulants, yeah, so because this is exactly what you expect for accumulants, you know that gamma would be theta squared. And you know that theta is usually 1/3, so that gamma would be 1/9. Yeah, that is what we would expect. And now what we could do is we can solve this under the condition that theta is equal to 1/3. And then we got to this much simpler solution here. Which, by the way, is almost, I mean, it's really crazy because I see, yeah, I don't know why we have this discrepancy here, but I show you something. So in this old solution, in the old wrong, so any of these may be wrong, yeah. In this old solution, if we put this, we get 3 plus 16 tau odd square plus or minus square root 9 plus 256, the 56 tau odd to the power of 4, and this divided by 48 tau odd. Now you would say this is completely different from what we see in the solution, yeah, and it appears to be different, but bear with me. So 4 tau odd much smaller than 1. So if we have a small diffusion, then this tau even will become roughly, so we'll eliminate these things, and we get what is left here is this 9. Yeah. So this will be 6 divided by 48 tau 0, which would be, now I'm running out of steam, 1/8 tau 0. So now the question is, are we so wrong actually? So you see, if tau 0 is going to, yeah, that's, I don't know why we don't get it exactly, but in principle we get the same result. Now there is I hate it. So there is something that is, sorry, that are called the magic parameters. They are called lambda even odd. That is tau e times tau odd. Yeah, and there is an old theory that you should keep this product constant. Yeah. So in order to have this product constant, we have to, if you we have to simplify it in this way. Yeah. And now we can put this to 1/8, and then we are not, because it is only an approximation. It's not exactly this. You could also use exactly this, suppose that it was exactly that. Yeah. But with this, you get supposedly something that is much better than using, for example, Beach and K. So we can also translate this for omega E. Yeah. So when I'm not showing this here because we have waited long enough. So omega E will be omega odd minus 2 divided by 2 minus omega odd plus 4 lambda even odd times omega odd. Yeah, so you plug whatever value comes out in here, you plug this into the even, and then the idea is that you now have a magic parameter and this can lead to surprising, so actually drastically better results. And this is without any computational costs. Because it's just a parameter. Yeah. So you get much higher accuracy by just setting one of the parameters differently. This you can pre-compute, and then it's all set. So how late is it? Oh my God. Oh my God. Now I know I screwed it a little bit, as always. The thing with all of this is I was actually prepared to implement it. You want me to implement it because it's our last chance, last meeting. Okay, I mean I'm completely over the top today. Why not? Let's get this implemented. Okay, so if anybody is not yet run away, you can anytime run away. I actually was thinking about getting even more fancy, because now we have done a diffusion, pure diffusion model, right? Built on raw moments. So suppose we want to have an advection diffusion model. So advection, what is advection diffusion? Going back. So here's lecture is over. Yeah. So what is advection diffusion equation? Would be very simple, that you have dtc plus velocity into c is equal to, let's see, tau odds theta Laplace c. Yeah. So you would have to have this here in addition. And the fun thing with getting this in addition is all you need to do is, instead of doing this in raw moments, to do it in central moments. When you get the velocity from somewhere else. So Now we have to implement, if we want to implement it. So if you insist on staying with me here, then we would have to use two lattice Boltzmann simulators, one for the velocity and one for the diffusion, advection diffusion. So because I'm lazy, I will do the following. We have already have this child variable, yeah, that we used for the multi-grid, not the multi-grid, the multi-resolution solution, yeah. So I will use exactly the same thing here. Just I have to be reminded that this time we need to have both of them the same size. Otherwise, it wouldn't work, yeah. So, and then we are going to, maybe we potentially need a few functions, but I don't know, I'll put myself somewhere here. Okay, now what I will put myself here. So I'm taking this run cumulant kernel, and in a very bad style, I will just take a copy of this entire kernel, including the swaps. So, okay, I'll take the entire thing here, copy, and I'm going to call this run run AD. Okay, so I will now, let me see, we need an addition, I think we need an additional relaxation parameter for this. To have, because we are now relaxing actually the first moments that we did not relax previously. So inside my time loop, what I'm going to do inside my time loop is I'm assuming that I set up the child for, I'm assuming that I set up the child for the fluid simulation, and then I do in the child I do a run cumulant, and I do this with one step. So I run one step, and then I put, actually there are matching parameters for the fluid thing too, which would improve the simulation, but I'm not going to do this here. Yeah, so this is something that did not fit anymore in the lecture. So just 1, 1, 1. Yeah. So then we have the one time step done. Then what we still need here, so we have only one conserved variable, and this is raw. So the other ones are coming from another place. Now, as I said, we want to derive the central moments, which kind of we have done here. But the central moments get the velocity from somewhere else. So what I'm going to do now instead of this is, which we have not yet done, we have not yet done the chimera transform. Yeah? So we are going to use chimera transform. I will not use the chimera transform in its most ideal way, because it's, again, it's complicated. So the chimera transform needs more variables. So we have to have what are chimeras? So we have a central moment, which we indicate by k, and we compute the central moment in the x component, and we keep the populations in the y component. So I need some sort of separator, which I don't have an idea. I just put an A here, because if I don't know about, usually in the lecture I had this operator, but this doesn't fit in C++, right? So I say I'm doing this for the minus part in the y direction, yeah? And I get the zero order moment. So how does the zero order moment look like? The zero order moment is here the sum of all of them. So this is f mm x and y, and I could actually put some brackets here to get ordered summation. Fm, why is it, doesn't it like it? It doesn't like it because it's not complete. So then p plus f 0m x and y. Okay, so this is in one dimension, yeah, this is the zero order moment, yeah, for everything that has in the x direction, in the y direction, a minus here, yeah. Okay, get out of my way. So now I have to repeat this 3 times. Because I also want this for p. That's p, p, p. And I also want this for 0. This is why I need here this divisor, because otherwise it becomes k. We cannot distinguish this anymore. So 0, 0, 0. So now I have the zero order moments. Now I want to have the first order moments. Therefore I will copy all of them. This makes more variables. In a serious implementation, you can do some in-place computation. This is now too fancy for us. So we now want to have the first central moment. So how do we get to the first central moment? Here we have to multiply with this thing here will have to multiply with -1, because it goes in the negative direction, yeah? But we also have to subtract the velocity, and the velocity is now the velocity of the child. So the child, okay, let me, so not to make too much mistakes here, try to use cheat sheet. So this is because we are doing this in x direction, this is the x velocity. The other guy here has this in plus direction, but the velocity here is the same, yeah. And the last guy has itself velocity 0. So I kind of have the impression, rather than doing this again here, I'll rather do this, and I'm going to replace everything here with a P. And I acknowledge that this can be done more elegantly if you would write in place function, what is this, functions for this, yeah. But let's not get too fancy. Now we have the first moment, and what it doesn't like is, what I doesn't like is this is artificial intelligence always trying to explain things. So with this, okay, let's get the second moment. So second moment looks like this, that we have a 2 here, and now this would be easier in Python. We get the square of these things, so I'll get the square by multiplying it with itself. So my acknowledgement, this can be done more efficiently by externally this, but okay, let's not bother too much with efficiency today. So that's again, we have to do this again by replacing all the m's with a p. And then we have this a third time, where we have to replace all the m's with a 0. So that's okay. I'm finally beating some. Sorry, no, that's not. We all love you. Sorry. Okay, now we are only halfway through. So we did this one way. Yeah. Now comes the other dimension, where we have to actually we need this again, k. So now we get k0, 0. So how do we get to k0, 0? K0, 0 is, now we have to add everything. So this here, and yeah, so basically we have to sum over these, yeah? So we'll get k0, 0 is k0 am plus k0 ap. So it makes sense to combine them, plus k0 a0. And that happens for the other guys too. So now this are all zero moment in this direction. Yeah. Now we have to do the first moment in this direction. And the first moment in this direction will have here again. So this is the minus, so it's -1. -1 minus child. Now it's the y velocity, so I guess we call the y velocity v, right? X and y. Yeah. X and y. So this here with a plus and here with nothing. Yeah. So now we have to repeat this 3 times. Because we want to have this here with 1, 1, 1, 1. Sorry that it is so boring. I know. It is so now we have all of these. Now we need the second moment here. The second moment we get by squaring these velocities. And hoping we are not doing any stupid nonsense. Not this. Yes. Thank you for. I pressed. Okay, so that's number 1. Oh, okay, I'm getting, we want to have this, let me see, we want to have, right, we want to have this with, yes, so that's, yeah, shout, you know, louder. So that means we'll have here 2. So now we have generated all of them. Yeah. I mean, obviously there are some things that we could that are doubled. Yeah. So that's not the efficient way of doing stuff. So now we need collision. So what do we do in collision? We do collision K01 is K01 plus I call this AD, yes. AD times, so equilibrium is 0, that means we get here just K1, we just get this, yes. So now the others look like this. Okay, so that guy is a second order, so we could here P, yeah? Wait. Equilibrium, and equilibrium is basically is rho. So we can, okay, in principle, it should be K00 divided by 3.0. Yeah? So then we have another one that, even though this is not necessary, but it's also second order, so I keep it with this one. But this has equilibrium of 0. And then we got these guys, they are third order. They also have equilibrium 0. So they look like this. And then there's one missing. And this goes by 9, if I recall this correctly. So, okay, so that would be the collision. Now, inverse Chimera transform is unfortunately something nasty. This is something that I skipped over so far. So what are we going to do to get an inverse? So first of all, we want to get from these, from K00 to these in the middle, yeah? So how do we do this? We do this the same way as always. We go here, take a new file. This is potentially a little larger, and say this was the transformation one way. Yeah. So I'm going to. I don't like to have this float here, so I will replace all the floats. I will replace all the semicolon with comma. And I will replace all the equal sign with equal equal. Then I will, okay, then I will keep this for later purposes and copy this here. And now I want to isolate let me see. So this is the first one. Did I do too much? Okay, no. Okay, I'll delete this one. I'll only keep, one of these. Yeah, that together make one. I think it doesn't like. Okay, it doesn't like the child. I replace this by nothing. Replace all. Okay. Now we solve this for K0AM, K0AP, and K0A0. So that's what is coming out. Okay, I don't. Since I do not particularly okay, I can make the following. Fortunately, we always have to do this like this. The thing is, the C form is going to destroy this again. So what is it? K0 AM, yeah? So we do K0 AM is equal to that thing here, and there's really no way to get it really. Yes, we need a child, yeah, but you know, the mathematica doesn't like this operator. Mathematica, the interpretation of mathematica with this is different. Maybe the so apparently, you know, programmers need something to get paid for. I don't know. You know, it's always semi-automatic, like a gun. Yeah. I mean, one thing that may actually be more useful is doing it like this, and then, because as you see, there's always one thing, KAP, K0AP. So, no! Okay, no, not doing it this way. Not, not doing it this way. We actually, I mean, this must be the use for artificial intelligence. Yeah, that just give me this in the appropriate form. I forgot the child. I know. Never forget your children. So one more, and then I try to speed this up by, so the 0. Okay, 0A0.
You can copy the whole thing.
The whole thing.
But the child.
I mean, that's, that can be, yeah. So, now how do we get this faster? So we get this to 1, 1, 1. The thing, this is 1, 1, 1. Stupid order. 1, 1. Okay, that could have been, yeah, pre-optimized beforehand. So, was this reasonable? Why are you not going home? I mean, that is. Okay, so we got. Okay, now we should have all the intermediates. Now we go to the other direction, right? And this can either be done by more thinking, or we in here no, this I have not copied this part. So we can it's always dangerous that so late I try to start thinking. So I think I don't think, and I just put these here. I'll take a new one. So I'll replace all the children with nothing. I will replace all the float with nothing. I will replace equal sign with this equal sign. Then I will replace semicolon with comma. And then I will take out of these, I will take only 3. Maybe that one, that one, that one. And then I'm going to solve this for FPMX Y F0M X Y and F, what is missing? MM. So then what do I need? F0 M X Y. So okay, it is stupid, but what should we do? No! Oh, no, 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 power. Oh. Find this so annoying. Yes. Okay, now we learned so here this is the second. So what did we ask for? F M0M, yeah? F0M X and Y is equal to this thing here. We need to have child. Okay, maybe I'm I'm doing this. I think this is faster when I'm doing it this way. You know what is even faster than that? Let me just FP so we have FP M X and Y equal to that. And then we have the FMM. So now I'll just do this. I'm going to do this only once. With U. Hmm?
You can also find and replace and use.
Okay. As you wish. So we have this here, and we replace it by this here. So, and then you mean all? Yeah, like this. Okay, thank you. So what we need semicolon. So there still is a mistake in this, but I will take care of this mistake later. Before I will now just go through all these possibilities again. So because we now want to do this also for P. Shall I use find and replace for this too? I think there is a big chance of making a mistake here, yeah. So you're watching out. If there's one mistake, we'll not see any result. P, yes. So now we need another 3. Actually, Chimera transform means more lines of code. It is still more efficient. So 0, get out of my way. Why didn't you say anything? I was missing this. So so amazingly, in principle, that should be all of them. Now, this was the previous thing that we now have to get rid of. And here we actually see that we did not write the correct results, yeah, because we have to put them in the post-collision version, which is coming here with an S, yeah, and whenever we have a minus an M here, we'll have a minus here, the +1 here, because we have this push scheme, right? Yes, S. S, so S -1, -1, S, big S, +1, S, +1, +1, S, -1, +1, nothing. Okay, so now we have a little bit. Okay, I keep this here, but the velocity has no meaning here, so I will multiply the velocity. I mean, we could discuss about this, but we have not set the velocity, so I kind of. Okay, you see, this is a very stupid way of doing things, but what is the time anyway? We have after. It's usually time to go home. I remind you that we wanted to have this lecture in the morning, yeah, originally. Okay, I will put here an additional boundary condition, yeah, I will put an additional boundary condition in an if maybe okay, if geo is equal geo x, so we have used 1 and 2 and 0, and I put now 2, and this is supposed to be a very simple source term. So for the density, yeah, because otherwise if we don't have any boundary condition, this doesn't look very interesting. So I will very simply propose that we have this here times rho. So whatever we have stored in rho will be put. I mean, this is the most simple thing I can think of, yeah. Just putting the density here. No idea how this is going to look like. Let us so we multiply this by the lattice weights. This is I'm keeping the lattice weights.
It's not necessary.
Okay.
It's a question.
question. So it is not necessary, but it will, you know, you get a very anisotropic yes, it's a very bad style. I mean, it's strictly speaking, it's not necessary. But asymptotically, yeah, but you're not getting a good you're not getting a good result. And then I have to explain again why it looks like this. And we don't get home, we don't get sleep, we'll and we die too young, and this is not good. So we need minimalistic, we need two more things. We need to set so we have to be able, could have set as you wish. So set source, and then we have to transfer this to where's the get so we have not compiled this once. Okay, now apparently, let me see whether this compiled it. So I actually have done some okay, I tried something out, yeah, but I now have to rearrange this. Okay, so this is a function that I've actually not implemented now. So okay, what did I? So we read this, and then I have something with columns. Then I have for the omega AD and for the lattice Boltzmann thing. Okay, put to the same. Then there is this. Okay, there is this equation. That equation that I wrote down in the in the lecture, and here this is 1/8. Yeah, so in principle that should be the thing. Then I apparently, so I said the child, where did I put the child? Yeah, get child. So I put it to 0, 0, and that's the same size. Yeah, so that it can actually run. Then I set some boundary condition. This is a lid-driven cavity thing. And here you made me call the source that this is how we know that I'm not using the one pre-compile that we actually see whether we implemented it. Yeah. Okay, and then I also have a AD. I need this again. Okay, so then we start this, and okay, so there is some old parts. What is going to happen? Okay, so what I put here, I put a source line here and a point line there. And I'm currently a little bit surprised by how long it takes to update this. And the result looks surprising. I would actually say it doesn't work. Why it doesn't? I mean, there is some. Okay, you see that something was happening. Is this? Steps. Okay, let me run this in singular time steps. There is something. I mean, this is potentially because it's recording, but it is too slow. I have to admit we somehow made a mistake. So today is really one of these days where I mess up everything. Let me see, what is run AD? Like we did not swap or something. But this also doesn't make sense because, you know, where's my, you know why this doesn't make sense? Because if we run it, you see that something runs. Something happens. Just there's nothing happening. There's nothing happening here. So the simulation runs, but somehow somehow my boundary condition didn't work. Oh, is this related to, I don't know, AD? Can I make there more diffusion? No, more diffusion. So if now, since we said more diffusion, we should see diffusion. We don't see diffusion, so there's something wrong in the code. There is. So yeah, that's always the challenge if you do such live things. So now here we are completely in the recursively running. So it compiled it. That's good. It actually Okay, maybe something with the if q equals. Okay, now it's your turn to rescue me. We could run. Have too many open tabs. Run refine. Run simple. So suppose.
Should this boundary, this set source plus equal, not just equal?
No, when it's. Okay, what I'm doing is I turn this off and see. Okay, yes. So there's something. Let me put it this. So now what we can do instead is just putting stuff there and then let it diffuse afterwards. So that's not so fancy, but at least it gives us. Okay, let's start it again and see that now we put some material here, we see some initial oscillations, and then we see some diffusion going away. But unfortunately, somehow this doesn't somehow, okay, we can set an initial value and then it moves around. I don't, but somehow our setting of the this is as if instead, you know why? Because it's 2. It's supposed to be 3. And if it is 2, you know what it did? It goes to the, yes, okay, to the other bounce back. So okay, that was the reason. So sorry for, yeah, okay, things, you know, you never get it. I mean, some people claim they get it, but I never get it without bugs. So let's put this boundary condition in here again. It's still compiling. It's actually still running. So now it has compiled. Now we restart this. And now we run it again. Now we have a source term here. Okay, I think in order to get something to see, I'll put more. The one problem that I have, and I checked this out, the boundary conditions is a bit problematic, yeah. So now the vortex in this simulation turns this way. So there's a downdraft here, yeah. And the velocity is not very high, because if the velocity is high, I get problems with the corners here for whatever reason. But what you already observe is that this is not diffusing in arbitrary directions, but is actually going going down here. Whenever we make recordings at the same time, it becomes incredibly slow. I'm trying to, let me see, I also have, I believe, okay, I made it very slow. So let me try to get this 10 times faster. hopefully without, yeah, you see, when I make it faster, I crash it. So in order not to crash it, I cannot afford, I have to go lower, yeah, with this. So apparently this is probably not the best model in the world. So now we have more diffusion. And yeah, so there's a downdraft on the left side with actually because the viscosity is also very relatively low. Yeah, so there is a positive source here and a negative source there. Now you can potentially see the vortex that is coming down this way. Yeah, so yeah. Now we, from our pure diffuse, now yes, the vortex is now also going up here, and then it's taking the negative part with it. So now just by using central moment instead of this raw moments, we got to an advection diffusion equation. Okay, what does it mean for time? It's 6:30. Any further questions? I think this time, even though there were a few mistakes, I'll try to give you anything that can be. I thank you for staying with us. Now this is for this semester. This is closed, and I will also stop the recording now.